So welcome to the Picture Language Seminar. We're very happy today to have Colin Wren. He's from MIT, and he's going to tell us about preparing states with anions. So, Colin, we're looking forward very much to your talk.
Thank you very much, Arthur. Hi everyone. My name is Yuanjie, also Colin. So, um, just a few more words about this series of seminars. This is a really good series. And if you look at the website, you will see that the first speaker this semester was Michael Friedman, and the next one will be Seth Lloyd. So you will know how good quality this series seminar is. And you will also know how much pressure a speaker can get as a student. So yeah, if you haven't subscribed to this series of seminar, please do so. And okay, here's my today's talk. I'm going to talk about preparing anions in the solvable theories with constant depth using adaptive quantum circuits. By adaptive, I mean that we should add of course, I'm gonna talk more about this. We're gonna add measurements and some feed forward to the local unitaries. And here are my collaborators. Don Williamson, he's affiliated to IBM, and also he's in University of Sydney, and also Nat. He actually graduated from here. I'm sure the participants, most of you know about them. And Nat right now is in Caltech. So here's the plan for today's talk. I'm going to start with motivations, and I will pay a lot of attention to those examples. Some of them are really simple, and hopefully those simple ones can get you familiar to the hard ones. And then I'll also go to formal theory behind this. And at the end, I'll talk about some outlook and some conclusions we can get from this work. All right, so we have known that different long-range entanglement in topological orders in topological physics can be classified using equivalence class defined by constant depth local unitaries. That work was started by Xie Chen and Zhengzheng Gu and also Xiaogang and around 2010. And basically it's saying that we can define equivalence class of topological orders if they can be connected by local unitaries and constant depth. So that's what this equation means. And now we can generalize this idea by including some measurements to the toolbox of the operations. This can define a more cross-grained classification through adaptive finite depth local unitaries. It's more cross-grained because finite depth local unitaries correspond to no measurements and hence no adaptive circuits. And so that will correspond to a different classification. For example, product states, ground states of the quantum double Z2 and double D4 and S3 can be seen as in the same class. However, a Fibonacci topological order is of another type. That work was captured by Ashwin's group in around 2022 and 2023. And the other motivation is that we can also view this sort of effort as a quantum simulation for topological orders or TQFTs, because such system can be used to encode logical information for QEC, quantum error corrections. And the advantage is that constant depth with respect to the distance of two different a pair of anions or separations will bound the number of qubits happened during the operation. So that's one of the advantage. And okay, here I'm going to start the first example. I'm sure a lot of you has already known about this. However, I will adapt a little bit different notation so that it aligns well with the Ising model. So instead of using just 0 and 1 for ordinary computational basis, I'll use the math boldface 1 to represent 0, which is the simple object in the category of Z2, or you can view this like graded vector space and use psi sometimes to represent 1. By 1, I mean the ordinary 1, 0, and 1. So, well, this example will serve as a warm-up to get us familiar with the notation later in the case of icing. So here, the equation 2.1 means that we're going to talk a bit more about this later, but it just means we can go to the icing category as the input category of a level 1 model by 2 steps of grading. So each arrow means 1 step of the grading. We're using 2 different Z2 groups. In the first step, we grade the trivial category, which is back. By grading them, we turn it into back Z2, which means it has 2 sectors graded by 0 and 1. The sector graded by 0 is the ordinary one without math boldface, and the sector graded non-trivially is the one that has a single object psi. So each sector has only a single element. And we'll talk about the icing case later. So let the Hilbert space be a tensor product of QDs on edges of the lattice. You can think of square lattice or whatever other lattice you prefer. And each local Hilbert space is just a single qubit as usual. And the easiest ground state, this is the easiest example of a topological order. And it's the superposition of all loop configurations. There are multiple. If we put it on a torus, you will know that it has 4 ground states. And let's just focus on the one that's the simplest, which has no underlying non-contractible loop. And the ground state will be an equal superposition, which means the faces in front of each state is just +1. And then we are talking about the summation over all various configurations. For example, one of the state will just have a single plaquette, and all the other parts are just nothing. And this is the other example of a configuration where it has 3 loops on the lattice. And the black part are just, in the computational basis, it's just 0, or in the categorical basis, it's math boldface 1. And the loops are in states psi. So that was the ground state wave function. And for the most of the time, I'll just forget about the normalization factor. Okay, so another way to write down the ground state wave function is actually by gauging or using the Krem's one-year duality that was introduced by Nat Rubin and Ashwin. So this equation is a little bit long. So let's slowly pay attention to the first equation. And to the right, we put this trivial states on the edges. Capital E means all the edges of the lattice. And then we use controlled X to just where control is on the center of the plaquette. Well, some people might prefer putting the control on the vertex. But however, we will be using level 1 model. So it's a dual lattice of the ordinary quantum double model. And that's why the control is on the center of the plaquette. And then for each control, we will try to flip all the vertices of this plaquette. All the edge qubits for this plaquette. And then this operation is done on all the plaquettes, so that's why there's a product over all P. And then for each plaquette P, we measure it to plus sign. Of course, there are 2 measurements, plus and minus. I'll talk about how to deal with that later. And the capital P just means all plaquettes. So that symbol means a product state of all plus in the X basis and over all plaquettes. So, and that's explained here in the second equation that explains what plus sign means. And right, so eventually we can get the same ground state using this duality map. And here I show a picture where you can view this as sort of a tensor network approach description for the ground state of toric code. It's exactly the same thing as the previous picture. Here I just fuse, these side loops to it, and here there are two neighboring red loops, and when they will fuse in a way that respect according to the fusion rule of the corresponding category, input category. So that means it will just fuse to the black edge, which means nothing. So exactly the two pictures correspond to each other. And so here, let's just pay attention to this controlled X. Later, we're going to replace this controlled X to something else for a more general case. And I mentioned there was issue that we could measure something minus. I mean, half of the time, the measurement a single plaquette P is in the minus state. And to deal with that, we just simply pair them up and apply a string of Z to correct them. And here the Z are just the ordinary poly-Zs in this case. And then later it will be some generalized Z or the character of the grading group. So we can talk about that later.
How can you ensure that they always appear in pairs?
Good question. So that's because this corresponds to the excitations inside of it. So our excitation can be paired up. And that's because we start from a trivial product state. And yeah, that's a very good question. So usually we could have some single excitation on the torus, but that won't happen here because we start from a product state, which has nothing interesting there. All right. So are there any other questions? Okay. So now I'm gonna move on to the icing model. I'm gonna talk about how to prepare this in constant depth. So back to the same equation. Now we pay attention to the second gradient. Basically, we cast the back Z2 category as the subcategory of the icing category, which means by subcategory, I mean it has a trivial grading. The grading is 0 in Z2. And then the extra element or extra simple object sigma has a grading 1, which is the only one that has a non-trivial grading in the second Z2. All right, so I'll use red color to represent that it has a non-trivial grading. And now, so unfortunately, I'm gonna skip the introduction about Lemon model. I just hope the audience capture what it means through this demonstration. But if you want to know more about it, you can just look at either Levenwin's original paper or the generalized Levenwin model, generalized string net model later by Levin. So here we define the BP operator, and it has two operators here. One is the trivially graded one. The other is the one that has non-trivial grading. You demonstrated by different colors. And here, as you can notice, we put some factor here, and that factor also appeared in original string net model. And the main purpose is to make sure that these operators form a representation of the underlying grading group. So that means if you square BP1, we get back to BP0. One can easily derive this from the fusion algebra. And so that corresponds to the sign operation in the Z2 group. So now I define a controlled plaquette operator where I put some ancilla at the start of the plaquette. And depending on I being 0 or 1, I fuse this loop. Either it's the loop is in the 0 sector, or it's a loop in the 1 sector. So that dependency is on I. So
I think online it's not possible for people to read that. So you have to say what you're pointing at.
maybe I can zoom it in. So
Pointing to the screen, people can't know what you're pointing at.
okay. So can people see my cursor?
Yes.
All right. Yeah. So that's so control is on the I qubit, and then BP will acting on the wave function that we care about. All right. Okay. Okay, now it works. So again, we can write down the same ground state wave function by using the corresponding Cross-manual duality, where instead of having a control X, remember in the case of toric code, we have control X where X is around the plaquette. Now we have control BP, which I just defined before. Well, you might be worried how do we implement this BP in real life? I'm going to talk about that later. So basically we just replace controlled X in toric code by controlled plaquette, and then make a product over all the plaquette. And again, we project it to the plus state regarding the grading group. And where the plus state are the acilas that we talked about in the previous set, that was the I here. So the plus will be 0 plus 1 over square root of 2. And then we apply this Cross-manual duality to the plus state, and that's how we get the Ising ground state in constant depth. So again, you will see a familiar picture where I just replace all the files in toric code into the sigma loops. It just means the same thing. We basically fuse the non-trivial grading part into the original topological order. Then we get the new topological order. So this fusion tensor network point of view will correspond exactly to the state configuration here. This is one of the example in the ground state. Here, the black parts or the trivial parts are no longer the trivial element in the tensor category. Instead, it's locally a toric code ground state wave function. So this part is the toric code ground state wave function, and they are here. And for the sigma loops, we are summing over all possible sigma loops. You can view them as domain walls, and they partition the whole manifold into several parts, and each part will be locally look like a ground state of toric code. All right. So how do we do this using quantum circuit? So I figured this out by using a similar approach as one by a paper in 2022. I think I forgot some of the authors, but I think one of the authors is Guanyu Zhu. Yeah, you can see the reference that I put today at the end of the talk. So here we are we're putting 6 qubits to the edges, or more precisely qubits to the edges, and we introduce some ancilas labeled by 12 and 13 and S. So S will correspond to the loop that we are fusing to the edges of the plaquette. And okay, let's do it right now. So we first apply a unitary that has that is supported on 0 and 12. And basically what it does, it copies the state on 0 to the state on 12. So you can think of it as similar to a control knot. control node exactly does similar thing by copying the controlled qubit to the target qubit. And then we apply a controlled F operator to the second figure. That's so if you're familiar with the F operator, you'll see here those are 0, 12, S, and here there is another S, but for practical reason we just remove it because it's the same state. So those are the two branches in the tree diagram. That's how we apply an F operator, and that will move this vertical edge to the horizontal one. That's what F symbol does exactly. And then we do another F move, and that will turn the second graph into third one. And we just keep doing the same thing. Eventually, we will fuse this loop qubit to the edges. And as you can see, we kind of shifting the edge qubits by at the beginning, the 0 is on top, 1 is here, 2 is here. At the end, 0 is moved here. So there's a translation around the edges of the plaquette. So that's how we deal with this controlled plaquette operator in real life. And is there any questions before I move to the next section? Okay, so I'm gonna talk about nilpotent anyon theory. I first need to define it. So for level 1 model with input category C, the anyonic excitation of topological orders are classified through the MTC, which is the centered category. That's a fact. So for the nilpotent case, there will be a series of gradient groups for and that will also correspond to a ascending series of the categories, which will it's such that the first category is a trivial one, and the last one corresponds to the center of the category, and each one is contained by one of the higher level. So, for example, BG, this MTC is can be decomposed by the gradient group GJ, and then it's trivial. There will be a trivial sector labeled by 1, and that will correspond to BJ minus 1, which is the MTC of a lower level. So that's how they're connected to each other. If for any anyon in BG graded by each element in GJ, there exists an kind of an inverse anyon with inverse grading each bar in GJ, such that their fusion product are all in the trivial sector, which means we can move to a lower level MTC. That then we say it's a nilpotent anyon theory. So this is really powerful constraint. It makes this theory really easy to prepare anyon in constant depth because it looks very similar to a billion topological order. So here is you can view this as another way to define it by a picture. So suppose we are trying to create an anyon AG, and at the far right side there's A bar and the inverse of G. And then we can create this anyon in constant depth, where here I show that I'm taking the series here at the beginning. We take the general K. Here, let's just restrict K to 3. So just by 3 steps, we can prepare it. And let's look at them, take a closer look. So at the beginning, we just create, let's say we try to create a length n ribbon. And then we just, by just putting n pairs of length 1 ribbon here, and each ribbon is a pair of AG and the inverse of that. And now let's fuse neighboring AG and the inverse. So let's pay attention to here. and forgot about the other parts. Suppose their fusion product is BH1 labeled by 1, and then by the nature of new potency, it must lie in the MTC of a lower level. So we simply go to a lower level MTC, and we don't need to worry about other anions in the highest level MTC. And then we create a pair of anions in the MTC of a lower level, such that this BH smaller and equal to 1. This is a complicated notation here. It just means H1. And we're fusing it to the trivial sector. And if we create a pair like this, all right. So, then we try to fuse here. So since we just created one, we must create another pair so that this anion fusing with this two will go to the trivial sector of the second level, which means it's MTC of the 2 levels lower. And then we keep doing the same exercise. Eventually, we create n-1 pairs of the anions of 1 lower MTC. And that finish up the second step. And keep doing this, we will get the trivial anions here. So then we have successfully create a pair of anion AG and inverse of AG in the MTC, original MTC. So one might worry that the fusion product, there could be several of them. How do we deal with that? So we will do a measurement, and that will constrain the superposition to be just a single specific anion after doing the measurement. So are there any questions in this process?
Is there any hope of actually achieving this in the lab?
I think as long as one can simulate an interesting enough topological order, then we can do this sort of exercise. So yeah, I think Liuan's work and Anna and Leo's work are related to that actually. So hopefully we can see that happen in real experiment. But I think the majority of the topological order we simulate right now are just the easiest one, which is toric code. So in that case, we don't need to worry about this sort of exercise.
Comment, the D4 topological order has been realized from trapped ion processor. And D4 is a non-abelian topological order, but it is nilpotent. So it's an example of sort of this intermediate, like it's sort of it's non-abelian, but it's sort of as close to being abelian as you can be.
I see. That's really cool. Have they released their paper or?
Yeah, so Continuum since last year.
I see.
Maybe people couldn't hear that. You could repeat that louder.
Right, and I just mentioned that Continuum has achieved quantum double of D4 last year. So that happened in real life already, which is a nilpotent theory as we described here. And as we mentioned before, nilpotent theories are close to a billion topological orders. All right, so thanks for the comment. I'm gonna move on to the next section. I'll talk about solvable anion theories. Again, let's define it first. So there will be a complicated mathematical definition, but here I'll give a simpler one, which is the physical version. So why do we care about this at all? So that's because in some anions, they're hard to fuse to get. So for example, the anion C, I need to talk about what C means. C here is the third anion, usually in quantum double S3, and it means the context class is the abuse of notation. The context class is the trivial one, and we're taking the representation of the of the S3 group to be the standard two-dimensional representation. And this anion has the following fusion rule. C times C will give us two other anions, which are easy to handle, but we get back C. And that means C is cyclic. So this has never appeared in our previous nilpotent theory. So we need to tackle this sort of problem. For audience who are not familiar with this, an excitation in the theory quantum double is labeled by a pair, as mentioned by a conjugate class of the group. And here, and then we need to choose a representative RC in that conjugacy class, and then take R to be one of the representation of the subgroup, which is the centralizer subgroup of RC, which just means group elements commuting with RC. Well, for a mathematician, you can just view excitation as a simple object in this tensor category. The solvable anion theory is defined by the following properties. So unlike nilpotent ones, this time the center is not graded. So, but the input category are still accepting a grading series. So there'll be, so this CK to the highest level is the very input category in level 1 model, and C0 again is the trivial category. So that's just the back. And let's say they have grading group G0 through GK. So one of the defining feature of solvable theory is that we can move from one center category to another to the neighboring one in the two directions. Going higher, we can gauge GI. Going lower, we can condense wrap GI. So one example is that the center of S3 can be obtained by gauging the Z2 charge conjugation symmetry of the Z3 topological order. So how do we prepare anions in ribbons infinite depths? The answer lies in, again, in the previous definition here. We can first condense it, and then we re-gauge it in the area that we care about. So here is a demonstration of how we deal with this solvable theory in general. It looks kind of like the previous one. However, here we're having this kind of error, which means we are gauging the one-form symmetry and measure the charges. And you can also say that we are condensing rep G. And so that helps us to go to the theory of one level lower. And then we do the same exercise by creating a pair of anions which fuse the previous one to the trivial sector. And then we need to introduce another pair which fuse the first two into a trivial sector. At the end, unlike the previous figure, we will have something extra deposited at the end, but we don't need to worry about that. We can continue this way, and eventually it has a string of deposited charges at the end, and we gauge it back to the original theory and just fuse that deposited charge to the one that we are creating. So that are the two different parts of this approach compared to the nilpotent theory. So of course, it's good to look at specific examples. Here we're gonna glance at the example S3, then we're gonna pay most of our attention to Tambara Yamagami. So here we're taking the lengths of the series to be 3, and between the first 1 and 2 is kind of trivial. So let's just pay our attention to the second step of the grading group. So grading Z2 will get us topological order of S3, and condensing Z2 will put it back. And the anion that we are concerned about is enel C, which upon condensing will become either electric charge E or its inverse E tilde. And that indicates that we can start from E or E tilde and gauge the Z2 part, then hopefully we can get create a ribbon of C and C bar, which is still C in the S3 topological order. So recall that in the Z3 toric code, the ribbon operator of E is simply a product of poly Z's in Q-trit. So let's set one be the state of this operator acting on the ground state. I'm missing here, there's a typo. I'm missing WSEZ3. S here just means the path or the support of these polys. For simplicity, you can think of S as just straight line with two ends. Then the claim is that after we use the previously introduced gauging process, we get a pair of C in the double of S3. So let's take a closer look. Those two operators are originally from Nat Rubin and Ashvin's paper, and let's break it into pieces. So the first line is still the Chromosome duality, as we introduced before. Here we're going back to the ordinary quantum double lattice, which means we're replacing plaquettes with vertices because we're going back to the original lattice. The reason is because most of the quantum double systems are put on the direct lattice instead of a dual lattice. And we are following that convention in the literature. So there are two blocks of this operator. The first block is controlled charge. I've demonstrated this part here, where for each vertex, we are it supports control, and then it's acting on the two neighboring. There'll be four, but it only acts on the upper one and the one to the right. So that's controlled charge conjugation. C is acting on Q-trace. It's just flipping 1 and 2 in Z3. And now let's pay attention to the second block. I put them in green. So the second block is just Chromosome duality we introduced before. And so this is the procedure that we prepare toric code. And while the two blocks does the following job. The first one is trying to couple the Z2 system and this Z3 system. And the second one is gauging the Z2 part, which will turn it into a toric code. So eventually this will become the S3 topological order. And so I'll skip the proof here. So eventually, if we start with these three, a pair of E enels in this three topological order, using this procedure, we will get a pair of C enels in the S3 topological order.
What are the two papers you're referring to?
So those are the papers by the same set of authors, and they are by Ashvin, Nat, and Rubin. So that happened 2 years ago and 1 year ago. At the end, I'm going to quickly show all the references.
So what happens if you get a minus result?
Oh, again, it's just we paired but now instead of using just a poly Z, here it's a generalized Z, which is the Z that corresponds to the gradient system. So for the Q-trit part, which means the 3 rotational part, then the Z looks like 1, 1, 1. And then for the other 3 elements in S3, which means sigma tau squared, and sigma, there will be minus sign. So we use generalized Z to connect. For example, we find a pair of minus signs. We connect them with these generalized Z operators. All right, that's a very good question. Yeah, I remember we talked about this. Back then I didn't understand, but now I understood. Is there any other questions?
Actually, sorry, just from like, I thought that it was, in this case, just a regular, is the minus charges, like if you get a minus result, it's just a Z2 charge, no? Or maybe I was, misunderstanding what you're measuring.
Yeah, so I can write down here. So here we use a generalized Z, which is not poly Z, but the Z for the grading group, the second Z2 grading group, which means, let's say, start from back to back. Here, this is trivial, and this is Z3, and so that'll be back at 3. So the grading group here is Z3, grading group here is Z2, and then the Z here will be E rotation squared, and sigma, which is flip part in S3, sigma tau squared. That'll be 1, 1, 1.
Okay, so it is just, but it's the tensor product of identity on the Z3 part and
Right.
as Z2. Like it is a Pauli Z, just tensored with
Right.
some
You
identity
can,
on the
yeah,
other.
you can see in that way, but it will not be a poly or anything like that. If for the async case, it will be the following. It will be +1, +1, -1, because this block is trivially graded. This block is non-trivially graded. Right. So we haven't finished the paper yet, but in the paper we'll talk about this. There'll be a set of projectors that these two measurements correspond to, and this generalizes will correct that. So those are excellent questions. Me myself was confused at the beginning too, but we dealt with this. So okay, I'm gonna move on to Tambara-Yamagami category. So just a crash course on this one. So Tambara-Yamagami has input, which is a building group. Actually, more rigorously, we should also put the character there, but let's say we're just picking one of the characters. And for this talk, I'll just focus on capital N equal 3. And the quantum dimension of these objects are the following. There are 2 sets of objects. The first N objects are just elements in these 3. And there's an extra one, which is sigma with quantum dimension square root of capital N. And those others are just having quantum dimension 1. And their fusion rules are following. First, they have just a Zn multiplication embedded in it. And if Zn element is taking product with sigma, it gets back to sigma. So, and if they are sigma multiplying together, we get a summation over all the elements. So as you can see, if we take n equal 2, that's just the ordinary async model, async category. So we will mostly focus on these 3, and we'll look at the G-cross breeding data. And those data are given by the Station Q paper and also in one of the Levin's paper. So by the definition of level 1 model or string net model, the ground state of Tambara-Yamagami category is given by fusing all possible B operators of all simple objects in this category to each plaquette. And there will be a weighting factor here. Again, I'm ignoring the overall normalization, but for each S, we're multiplying it with its dimension. As one can guess, this can be, that's kind of the whole point of this talk. This can again be prepared by the same protocol as we defined before, with introducing with plus and CLUS in the plus state on each plaquette, and we input these three topological order ground state wave function, or you can have some excitations as I mentioned about the S3 case, and do the controlled plaquette operator, and then project them to the plus state for each plaquette. For each plaquette P, half of the time we don't touch the original topological order, and the other half of the time we fuse sigma loop to P. We've seen a similar figure before. Here, well, to know the ground state wave function, well, hopefully after this talk, the audience will not only know the wave function of a toric code or double semion model, those easy ones, we also know clearly what the ground state wave function is for Tambara Yamagami category. So here's a formula where phi gamma, where gamma are those red loops, we're picking a specific picture. That means here in the picture we fixed gamma, and there are two gammas. One is smaller loop, the other is a bigger one. And those gamma labeled by I will partition the whole manifold into several parts. And for each part, I label them with J, letter J. And for each set of this gamma, there will be a factor phi of gamma. So that's a factor. I'm gonna later define what this factor is. And these two parts are the quantum states part. So gamma are the qubits supporting those red loops, and also the peripheral ones. And also here, this part will just be the ground state of these three topological order. Locally, it looks like a ground state of the previous topological order for each area J. And now I'm gonna define phi of gamma I, which is the ith red loop. So that's actually turned out to be a product of all the factors, which I call GV here, over all vertices of this red loop gamma I. Now, how do we get this? So first, GV is just square root of the third root of unity. It's either third root of unity or the conjugation of it. And why do we have this factor at all? So let's say we're fusing two red sigma loops to these two plaquettes, and before there was a K loop. I'm using the tensor network language of level 1 model again. We're gonna fuse these three to the edges. And then recall the fusion rule. That means this two sigma fusing to this edge E will give us an equal superposition of summation of all elements in Z3. And by calculating the F symbol, I've done the work. So we will get this one. And this one will just read off this factor, omega to the power of minus K, which was the loop here, where K belongs to this three, and B. Recall that B is one of the fusion product in sigma times sigma. And here are some, some square root of quantum dimensions that we don't need to worry about here. So that explains the factor here. So, the takeaway is that the ground state of Tambara Yamagami is superposition of all possible sigma loops, and those partition the manifold. And in each partition, it looks like locally like a toric code of Zn. And there will be those gluing factors. Those are phase factors around this sigma loop. And we just multiply those factors together. Well, to see the deep relation between them, let's take a second look. I'm running out of time, so I'm gonna skip some of the parts, and hopefully we get to the end. So we can divide these three toric code because it doubled, we can divide them into two sectors, one by this and the other by these elements. They're grouped together by the invariance of variance under EM duality. So we're cutting them into two layers of things. We're gonna pay attention to this one and forget about this one because we're gonna use the EM duality to help us get the Tambara Yamagami category. So that's why. So upon introducing the sigma defect, which were the sigma loops, red sigma loops, and we say that we are in the defect SET that enforces the EM duality, and we classify the objects by their orbits under this action. So those are three orbits, and they correspond to centralizer groups Z2, Z1, which is just a trivial group, and Z2 again. And then we choose the representations. For the first one, there are two representations which correspond to two anyons in the center of Tambara Yamagami of these three. Those are the first group. And for the second group, it's a trivial group, so it has only one representation. The last one is Z2. It has two representations. I'm gonna just spell out these facts. And they have the following fusion rule. Let's just pay attention to the phi anion because it has a cyclic fusion rule going back to phi itself. So the picture is very similar to the double S3. And because this is the hardest one, we only talk about this one. Together, we can identify those objects with the transaminase model of SU to 4, where we're taking K to 4. And again, here is the identification. So recall that there's another half of the system that we're ignoring. That's the Z1 copy. It's because it's invariant under EM duality. Eventually, the whole center category of Tambara Yamagami is stacking of the copy that we're not touching and the category we just got.
Yeah, I have a question. So isn't that you need to use a lot of this F move to realize all of that? As we know, maybe in Juice paper, they also use a lot of F moves.
Yes, indeed.
How easily you can realize these F moves in some systems?
It's not too hard because the one that I gave looks complicated, but in reality, we can do it simultaneously. I do it one in the same order as Levin Wen's paper, but in practice, we don't need that much ancillas because, for example, the S loop in the middle, it has a fixed state. It means we don't really need that ancilla. And there are also ancillas we don't really need. So the pedagogical approach that I showed is actually something extra. In reality, it can be done in a simpler way.
But this F actually requires some very non-typical gates. Right?
So
some complicated gates, and then if you want to realize that, you actually need some like basic universal gates to simulate it very greatly. And then
yeah, exactly. So those can be some complicated unitary because F matrices are unitaries. Yeah. The total number of excitation, therefore, is just tripled to number 15. That aligns with mathematical literature. So now the question is, what does string operator look like? So I'm gonna skip. So I only have 5 more minutes, right? Yeah, I'm gonna skip the explicit expression and just talk about the result. So that's a half-breeding data. Those equations are stored from, I think they appeared in Levin's paper. And then a ribbon operator acts on in this way. So, so I'm gonna zoom in. There are 2 types. Okay, actually, I'm gonna skip this calculation. And the takeaway is that we can do this explicitly. And as you can see, each partition part AK has a string operator that looks like a em star string plus e star m string. And that's exactly the relation between these three topological order and Tambara Yamagami. So okay, I'm gonna skip the details. So that's the theory of defect tube algebra. That first appeared in Dom's paper in the year of 2017. So we can use this to define the domain wall subalgebra, which gives us a projective representation of the grading group. That's a strong constraint that helps us to fix some of the defect tube factors. And then we can define clearly what the controlled plaquette operator is, and for the Kramswanian duality. And equation 8.7 is a conclusion equation where we start from an equal superposition of em string star and em string, em star string and e star m string, and then we do the gauging. Eventually, we'll get the operator that we care about, which was hard to prepare, but now it's kind of easy. Can be prepared in just finite depth. And now I'm going to move on to a summary. So we extend the idea of preparing ground states via gauging to preparing all solvable anyons in finite depth. We worked out three important examples, Ising, S3, and Tambara Yamagami. We conjecture this construction captures all 2D topological faces that can be created exactly via adaptive finite depth local unitaries. And we propose the following questions that can be studied in the future. Can we prove the aforementioned conjecture? Or can we prove that all topological faces connected to the trivial face under AFDLU, adaptive finite depth local unitaries, are solvable anyon theories and we get nothing extra? And the second question is maybe just prove that, an easier question. We just prove that single non-solvable phase, for example, Fibonacci theory, or of a non-solvable group lies outside of the reach of AFDLU, which is the equivalence class we talked about today. Or we can try to prove the equivalence class. Recall that AFDLU defines the more coarse versions of FDLU. And does that imply that, the equivalence class corresponding to MTC of FDLU correspond to the MTC modular tensor categories, since it's more coarse-grained. Does that correspond to MTC modding out condensing plus gauging processes? And also, Nat also mentioned that the equivalence class seemed to give some generalization of the weight group to some weight monoid. I don't exactly know what that means. Can these protocols be made fault tolerant for scalable practical QC implementations? So those are things that can be done in the future. I thank you all for your attention.
I think what I asked you is about the last point. I asked you about this case of this F node.
Yeah, for a generic, F matrix the gate, I think there's no reason that it has to be easy. So yeah, it could be some hard gate.
So thank you very much, Colin. Maybe we should stop sharing your screen and ask if there are any questions. So are there any more questions here?
It's very interesting that this room has gathered the correct people that care about this project. I'm happy to see familiar faces here.
Are there questions online?
Yeah, before people leave, I think Anna Liu also will release. Have you guys released your work? Okay. They will also release relevant work on this project, on this direction. So stay tuned to their work.